All right, let's jump right in. I want you to imagine a high-stakes mission, a real heist, but this one is happening on a molecular scale. Our target isn't gold or jewels. It's a tiny, tiny piece of code, a gene, locked away inside a strand of DNA. And our job? We're going to get it out.
And that's the big question, right? I mean, you can't just reach in and grab a gene. You need a plan. You need some seriously specialized tools, and you have to be unbelievably precise. So today, we're breaking down the playbook for one of the most incredible operations in all of biology, gene cloning.
You know, every great heist starts with a solid plan. So, first things first, we've got to understand our target. That's the blueprint, and the amazing tools we'll be using to pull this whole thing off.
So here's the game plan in a nutshell. Our target gene, that's the precious cargo. The getaway car, it's this little circular piece of DNA called a plasmid. And the final destination is a bacterial cell, which we're going to turn into our own personal copy machine. It sounds simple, but the execution is just brilliant.
And here's the catch. We are working at a scale that is almost impossible to wrap your head around. The success of this entire mission hinges on these cleverly designed enzymes that act like microscopic scissors and glue, and a few really ingenious chemical tricks. All right, let's get to our first big challenge, getting our cargo loaded securely into the getaway car. Now, this isn't about brute force, it's about a perfect, elegant, molecular handshake.
So, on one side, we've got our target gene, which we've already made millions of copies of using a technique called PCR. And on the other, we have our specially prepped getaway car, a T-vector plasmid. The mission now is to join these two pieces together, seamlessly.
And the way we do this is just so smart. It's a technique called TA cloning, and it's this really elegant solution that relies on the most basic rule of DNA. A always pairs with T. Scientists have basically engineered our two pieces to take advantage of this fundamental fact of life.
And here is the secret sauce. The special enzyme we use to copy our gene, it's called Taq polymerase, has this really neat little quirk. It automatically adds a single A, an adenine, to the end of every copy it makes. So knowing this, scientists designed the plasmid to have a single T, a thymine, just sticking out. They're literally made for each other.
So picture this. You've got the gene floating around in solution, the plasmid is floating around, and then they find each other. That sticky A end is drawn to the sticky T end. They line up, they form a natural hydrogen bond, and click. The key just slides right into the lock. It's our first big success. But that little click isn't permanent just yet. To really seal the deal, one final player has to enter the scene. An enzyme, something like DNA ligase, comes in and acts like molecular superglue. It seals the backbone of the DNA, making the connection permanent. The getaway car is now loaded, locked, and officially a recombinant plasmid.
Okay, phase 1 is complete. But now for the really tricky part, the infiltration. We have to get our plasmid past the defenses of the bacterial cell and deep inside the factory. And this calls for a pretty dramatic tactic called heat shock. So here's how the assault goes down. First, we chill the bacterial cells on ice with some calcium chloride. This basically neutralizes their outer membrane and makes them a little bit vulnerable. Then we add our plasmids. They just drift close, kind of waiting for an opening. And then comes the critical moment, a sudden, intense blast of heat followed by a lightning-fast return to the ice. So what does that blast of heat actually do? Well, that sudden temperature change literally rattles the cell's membrane, creating these temporary little holes or pores. And in that split second, our plasmid, which has been waiting right outside, just slips through the gap and right into the cell. It is a dramatic, forced entry.
And just like that, the infiltration is a success. Our code is inside the factory. But the heist isn't over, not by a long shot. We now have a brand new problem. Not all of the bacteria actually took up our plasmid. In fact, most of them didn't. So, on to the final act. We need to find those few successful bacteria that are hiding in a massive crowd of millions of failures. So how do we do it? Well, we make them show us their true colors. We take all the bacteria, spread them out on a petri dish, and just let them grow into these little colonies. Now, each colony is a huge family of clones that came from a single starting bacterium. But which family is the one we're looking for? How in the world do we find our prize?
The answer is in the color. It's a method called blue-white screening, and it's genius. Some of the colonies will turn blue, and others will stay white. The blue ones, those are our failures. But the white ones? The white ones are our jackpot.
So why blue? What's going on there? Well, the plasmid was designed with a special gene in it called LAC-Z. If that gene is working, it makes an enzyme that's basically a tiny color factory. When that enzyme finds a chemical we've put in the dish called XGAL, it chops it up and creates a bright blue pigment. So a blue colony is basically telling us, hey, the LAC-Z gene is working just fine, which means our target gene isn't in there.
But the white colonies, this is where the magic happens. In these bacteria, our target gene successfully jammed itself right into the middle of that LAC-Z gene, basically breaking it. So the cell can't make that blue-producing enzyme anymore. The XGAL is just left alone, totally untouched. The colony stays white. And that, right there, is our visual confirmation. Mission accomplished.
You see, that single white colony is everything. It's the signifier in the dark. We can now physically pick that one colony, put it in a big flask to grow, and it will become a factory, just churning out millions upon millions of perfect copies of our target gene.
You know, it's just an unbelievably powerful idea when you think about it. All that work, all those clever molecular tricks, it all leads to this one single identifiable success story. And that success opens the door to everything from developing new medicines to understanding the deepest secrets of life itself.
So the heist is complete. We've stolen the code and we've made our copies. The final question is, what do we do with it now? What mysteries can we solve with it, and what new questions are we going to uncover? Because that, my friends, is where the real adventure begins.